In the autumn of 1940, inside a building overlooking the East River, two men leaned over a row of test tubes and noticed something that would trouble science for the next century. Settle in tonight, wherever you are. Pull the covers a little closer, let the room go soft around you. This is a long, slow story, the kind that moves through laboratories and mountain villages, through ancient bloodlines and hospital wards lit by fluorescent light. It begins not with a grand announcement, but with a small glass tube held up against a window in New York City, and a man who had already changed the world, once wondering if he was about to do it again. The Rockefeller Institute for Medical Research stood on the east side of Manhattan, a cluster of quiet buildings set back from the noise of the avenues. In 1940, the city beyond those walls was loud with taxi horns and newspaper boys shouting headlines about the war in Europe. But inside the laboratories, the air smelled of disinfectant and warm glass, and the loudest sound was usually the scratch of a pen across a notebook page. Karl Landsteiner worked in one of those laboratories. He was 72 years old, thin, meticulous, and already famous. A decade earlier, he had received the Nobel Prize in Physiology or Medicine for a discovery that had saved countless lives. He had proven that human blood was not all the same, that it fell into distinct groups he labeled A, B, and O, and that mixing the wrong types during a transfusion could kill a patient within minutes. That discovery had transformed surgery. Before Landsteiner, a blood transfusion was a gamble. Doctors would connect the vein of a donor to the vein of a patient, hope for the best, and sometimes watch the patient convulse and die on the table. After Landsteiner, they could test, match, and proceed with confidence. The mystery of why some transfusions saved and others killed had been solved with a few drops of serum and a microscope slide. Mind. But Landsteiner was not a man who rested on achievements. He had moved from Vienna to The Hague, then to New York, always following the questions that would not leave him alone. By 1940, he had spent years studying the finer chemistry of blood, mapping smaller and smaller differences between human samples, as though the red cells under his microscope were a language he was still learning to read. His colleague that year was Alexander Solomon Wiener, a younger serologist with sharp eyes and a talent for immunology. The two men had designed an experiment that seemed, on paper, almost routine. They would inject red blood cells from rhesus macaque monkeys into rabbits and guinea pigs, then collect the antibodies the animals produced. Standard immunological procedure, the kind of work that filled notebooks with predictable results. The rabbits did what rabbits do when confronted with foreign proteins. Their immune systems recognized the monkey blood cells as invaders and manufactured antibodies to fight them. Wiener collected the serum carefully, labeling each vial with the date and the animal's identification number. So far, everything followed the expected pattern. The surprise came when they tested those rabbit-made antibodies against human blood. Wiener pipetted a small amount of the serum onto a glass slide, added a drop of human blood, and watched through the microscope. In most samples, the red cells clumped together, stuck to one another in that unmistakable pattern called agglutination. The antibodies had found something on the human cells that matched what they had learned to attack on the monkey cells. But roughly 15 out of every 100 samples showed nothing. No clumping, no reaction. The red cells drifted past each other in the serum, as though the antibodies were invisible to them, or they to the antibodies. Something that most human blood cells carried on their surfaces was simply absent in these samples, like a lock missing from a door that every other door in the building possessed. Landsteiner had seen enough surprises in his career to know when he was looking at one. He and Wiener tested more samples, widened their pool, checked and rechecked. The ratio held. Approximately 85% of people carried this newly identified protein on their red blood cells. 15% did not. They named it the Rh factor, after the rhesus monkeys whose blood had helped them find it. If you carried the protein, you were Rh positive. If you did not, you were Rh negative. A simple binary division, clean and clinical, drawn across the entire human species like a line in wet sand. At first, it seemed like a footnote, a refinement of the blood-typing system that Landsteiner had built decades before. Another variable to track, another column on a hospital chart. But even in those first weeks, something about the numbers unsettled the researchers. 15% was not a trivial minority. It was not a rare mutation appearing once in 10,000 births. It was nearly 1 in 6 people walking the streets outside the laboratory window. And the protein they were missing was not some minor decoration. It was ancient. Virtually every primate species ever tested carried some version of it on their red blood cells. Chimpanzees had it. Gorillas had it. Orangutans, baboons, every monkey Landsteiner and Wiener had examined carried it as faithfully as they carried hemoglobin. It was woven into the primate lineage like a thread running through millions of years of evolution. Yet 1 in 6 humans simply did not have it. As though somewhere in the long corridor of human ancestry, a door had quietly closed, and 15% of the species had walked through without that particular piece of biological inheritance. No one had noticed until now. No one had thought to look. Landsteiner recorded his findings in his careful handwriting and returned to his bench. He would not live to see how far the questions reached. 3 years later, in June of 1943, he suffered a heart attack in his laboratory and died at 75. His last experiment, it was said, was still in progress on the bench beside him, unfinished, as though the work simply could not wait. He left behind a puzzle that was only beginning to reveal its shape. The Rh factor was not merely a laboratory curiosity. It touched pregnancy, disease, survival, and the deep architecture of human migration. But to understand just how dangerous that small missing protein could be, the story had to move from a quiet bench in Manhattan to a hospital ward where a young woman had just lost her baby and was about to lose something else. Chapter 2, the first clue hidden in a stillbirth. A year before the Rh factor had a name, a mother's blood turned against her husband's, and a young immunologist began to understand why babies were dying. The case that changed everything had actually arrived a year earlier, in 1939, at a hospital in Newark, New Jersey. It reached the desk of Philip Levine not as a grand scientific problem, but as a clinical emergency, scrawled on a chart in a doctor's hurried handwriting. A young woman, 25 years old, had delivered a stillborn baby during her 33rd week of pregnancy. The infant weighed barely more than a pound. It had arrived into the world already gone, its small body emaciated, its skin the faint yellow of jaundice. The attending physicians recorded the details with the practiced brevity of men who had seen this before. Stillbirths were not uncommon. The reasons were often unclear. They turned their attention to the mother, who was bleeding dangerously and needed a transfusion to survive. Her husband offered his blood. They tested his type against hers. Both were Group O, a perfect match under the ABO system that Landsteiner had established decades earlier. The doctors connected the transfusion line, opened the valve, and watched her husband's blood begin to flow into her veins. Within 10 minutes, she was in agony. Her body seized with chills. Pain radiated through her head and down her legs. Her temperature spiked. The transfusion that should have saved her was tearing through her system like poison, her immune system attacking the incoming blood cells with a ferocity that made no sense. The doctors stopped the transfusion immediately and scrambled to stabilize her. She survived, but barely, and the question hung in the ward like smoke after a fire. How could her body reject blood from her own husband when their types were the same? The case found its way to Philip Levine, an immunohematologist who had trained under Landsteiner himself years earlier at the Rockefeller Institute. Levine was meticulous, cautious, the kind of researcher who distrusted easy answers. His colleague on this case was Rufus Stetson, a physician who had first noticed the anomaly and saved the blood sample, sensing that something important was hiding in it. Levine tested the mother's serum against her husband's red blood cells using a more sensitive technique than the standard bedside match. The reaction was clear. Her serum attacked his cells, binding to them and triggering agglutination, even though they shared the same ABO group. Something else was different between them, something the existing classification system could not see. He widened the test. He took the mother's serum and ran it against blood samples from over 100 ABO-compatible donors. 80 of the 104 samples reacted. The mother's antibodies recognized something on those cells and mounted an attack. But 24 samples passed through untouched, invisible to her immune response, as though they spoke a language her antibodies did not know. Levine and Stetson published their findings in the Journal of the American Medical Association in the summer of 1939. Their paper was brief, careful, and carried a title that gave nothing away. They described the case, presented the data, and drew a measured conclusion. There must be a blood group antigen that had not yet been identified, one that was present on most people's red cells but absent on the mother's. She had been sensitized to this unknown antigen, probably during her pregnancy, and her immune system had learned to destroy any cell carrying it. They did not name the antigen. They did not connect it to the rhesus monkey experiments that Landsteiner and Wiener were conducting just across the river in Manhattan. That connection would come later, when the two lines of research converged and the antigen Levine had glimpsed in a Newark hospital ward turned out to be the same protein that Wiener was finding with his rabbit serum. The Rh factor, the same marker, the same 15%. But Levine had seen something else in that Newark case, something that would prove even more important than the discovery of a new antigen. He had seen the mechanism by which a mother's body could be turned against her own child. The stillborn baby had likely inherited its father's blood type, carrying on its red cells an antigen that the mother's cells did not possess. During the pregnancy, small amounts of the baby's blood had crossed into the mother's circulation, and her immune system had responded the way immune systems always respond to foreign invaders. It had built weapons. Those weapons, the antibodies now circulating in her blood, had not only attacked her husband's transfused cells, they had almost certainly attacked the baby itself, crossing the placenta, entering the fetal circulation, and destroying the tiny red blood cells one by one. The stillbirth was not bad luck. It was immunology. The mother's body, programmed by evolution to protect her offspring, had been deceived into destroying it. Levine spent the next 2 years building the case. He studied more pregnancies, more mothers, more patterns. In 1941, he published a landmark paper laying out the full theory. The Rh antigen, now formally identified and named thanks to Landsteiner and Wiener's work, was the culprit. When an Rh-negative mother carried an Rh-positive baby. The stage was set for a war that neither side had chosen. Doctors across America and Europe read his paper and felt the floor shift beneath their feet. For decades, they had been watching a disease they called erythroblastosis fetalis, a devastating condition that struck newborns, particularly second and third children, with severe anemia, jaundice, and swelling. Many of these babies died within hours of birth. Others survived with permanent brain damage. The pattern had been visible for years, recorded in medical journals and parish ledgers, but the cause had remained hidden. Now they had a name for it, they had a mechanism, and they had a terrible arithmetic. First pregnancies were usually safe, because the mother's immune system needed time to recognize the foreign antigen and build its response. But once sensitized, those antibodies did not fade. They waited in her bloodstream like sentries, and if the next pregnancy also produced an Rh-positive child, they crossed the placenta and began their assault before the baby had taken its first breath. In the maternity wards of the 1940s, the new understanding brought clarity, but not yet comfort. Doctors could now predict which pregnancies were at risk. They could test mothers, identify the ones who were Rh negative, and watch with increasing dread as second and third pregnancies progressed. But they could not stop the antibodies. They could not undo the sensitization. They could only wait and hope and sometimes perform desperate exchange transfusions on newborns, replacing the infant's entire blood supply to flush out the maternal antibodies before they destroyed too many cells. It was brutal medicine, performed on babies weighing only a few pounds, in an era before modern neonatal intensive care. Some survived, many did not. And in homes across the Western world, families who had never heard of antigens or immunoglobulins buried child after child, never understanding why their first baby had lived, and the ones that followed had not. The question that no one could yet answer was the simplest and the strangest of all. If this blood type killed babies, why did it still exist? Evolution was supposed to be ruthless about removing traits that harmed reproduction. A mother whose immune system destroyed her own offspring should have been selected against, her genes quietly erased from the population over thousands of generations. And yet, Rh-negative blood persisted, common in certain populations, reaching frequencies that defied easy explanation. Something was keeping it alive, something no one had found yet. The answer to that question would take decades to approach, and it would lead far beyond the walls of any hospital, back through the centuries to mountain villages and royal courts, and deeper still into the ice and silence of a world that existed long before any human hand had learned to draw blood into a glass tube. Chapter 3: The War Inside a Mother's Body. Inside the womb, two bloodstreams run side by side, separated by a barrier thinner than paper. When that barrier fails, a mother's protection becomes a weapon she never meant to carry. To understand what happens when an Rh-negative mother carries an Rh-positive child, you have to shrink yourself down to the scale, where a single red blood cell looks like a small planet. At that scale, the placenta is not a simple wall. It is a vast, intricate landscape of branching vessels and tissue, a living border between two nations that share a body but carry different flags. The mother's blood flows on one side. The baby's blood flows on the other. They do not mix. Instead, nutrients and oxygen pass through the tissue between them, crossing from mother to child like goods traded across a river too wide to bridge. Carbon dioxide and waste travel back the other way. It is an arrangement of extraordinary elegance. Two circulatory systems running in parallel, exchanging everything the baby needs to grow without ever truly touching. For most of the pregnancy, this separation holds. The Rh-negative mother goes about her days unaware that inside her, her child's blood cells carry a protein her own cells have never known. The baby develops in darkness and warmth, fed by a body that does not yet recognize the difference between them. Weeks pass. Months pass. The belly swells. The heartbeat on the monitor is steady and small. But the placenta is not perfect. It is alive, and living tissue is fragile. Tiny breaks occur, especially late in pregnancy, when the growing baby presses harder against the uterine wall. Microscopic amounts of fetal blood sometimes slip through those breaks and enter the mother's bloodstream. A few cells, barely enough to see, drifting into a river that has never encountered them before. If mother and baby are both Rh positive or both Rh negative, nothing happens. The mother's immune system glances at the fetal cells, recognizes the familiar protein patterns, and moves on. But if the mother is Rh negative and those stray fetal cells carry the Rh positive antigen inherited from the father, her immune system encounters something it has never seen. A protein that does not belong, a molecular shape that registers as foreign. The first encounter is usually slow. The immune system does not respond instantly to every unfamiliar molecule. It takes time to identify, classify, and mount a defense. For most first pregnancies, the baby is born before the mother's immune response fully develops. The child arrives healthy, pink, crying, and the small invasion of fetal cells is cleared from the mother's blood without consequence. Everyone goes home. Everyone believes the danger has passed. But the immune system has a long memory. Deep in the mother's bone marrow and lymph nodes, specialized cells have recorded the encounter. They have cataloged the shape of the Rh antigen, built a template, and filed it away. If those cells ever encounter that antigen again, they will not hesitate. They will not need weeks to prepare. They will respond within hours, flooding the bloodstream with antibodies designed for one purpose only: to find and destroy anything carrying that protein. The second pregnancy begins like the first. An Rh-negative mother, an Rh-positive father, another child growing quietly in the dark. But this time, the mother's blood is not naive. This time, the antibodies are already there, circulating, waiting. And these antibodies, a class called immunoglobulin G, are small enough to do something that most antibodies cannot. They can cross the placenta. They drift through the tissue barrier like smoke through a screen, entering the fetal bloodstream one by one. Once inside, they find what they were made for. They bind to the Rh proteins on the baby's red blood cells, coating each cell with a molecular tag that marks it for destruction. The baby's spleen and liver, still developing, begin to break down the tagged cells. Red blood cells are destroyed faster than the tiny body can replace them. The baby becomes anemic. Oxygen delivery drops. The heart, still no bigger than a walnut, begins to work harder, pumping faster to compensate for the falling number of red cells. The liver swells as it tries to produce replacement cells outside the bone marrow, a desperate measure that healthy bodies never need. Fluid accumulates in the body cavities, the abdomen, the chest, the spaces around the heart. The skin takes on a yellow tinge as bilirubin. A breakdown product of destroyed red cells builds up faster than the immature liver can process it. Doctors called this condition erythroblastosis fetalis, or hemolytic disease of the fetus and newborn. In its mildest form, it produced jaundice that could be treated with light therapy after birth. In its most severe form, it produced hydrops fetalis, a condition in which the baby's body filled with fluid so completely that survival was nearly impossible. Between those extremes lay a range of suffering that depended on how many antibodies the mother produced and how early in the pregnancy they began their attack. Before modern medicine, the outcomes were often devastating. Medical journals from the first half of the 20th century record case after case, with the clinical detachment that hides human grief behind Latin terminology. A woman in Philadelphia who lost 4 consecutive pregnancies after a healthy first child. A family in London where 3 infants died of severe jaundice within days of birth. A rural doctor in France who noted in his ledger that a certain mother seemed cursed, each baby weaker than the last, each burial smaller than the one before. The cruelty was compounded by the pattern. First children survived. Second children sometimes showed symptoms. By the 3rd or 4th pregnancy, the mother's immune response had grown so strong, so practiced, that the attack began earlier and struck harder. Families who wanted large broods, families who loved children and planned for them, were the ones most likely to suffer. The very act of successful reproduction sensitized the mother's immune system, making each subsequent pregnancy more dangerous than the last. By the 1940s, doctors understood the mechanism well enough to predict which pregnancies were at risk. They could test a mother's blood for Rh antibodies, measure their concentration, and estimate the danger to the fetus. But prediction without prevention is a special kind of torment. Obstetricians in teaching hospitals would gather around charts showing rising antibody levels and calculate the odds, knowing that beyond a certain threshold there was little they could do except deliver the baby early and attempt to save it outside the womb. Exchange transfusion became the primary treatment. Within hours of birth, doctors would slowly withdraw the newborn's blood and replace it with Rh-negative blood, flushing out the maternal antibodies before they could destroy more cells. The procedure was delicate, terrifying, and often performed on infants weighing less than 5 pounds. In rooms where the equipment was barely adequate and the margin for error was measured in milliliters. Some babies survived and grew into healthy children who never knew how close they had come. Others did not survive. Others lived but carried permanent damage. Neurological injuries, caused by bilirubin crossing into the brain during the critical hours before treatment could begin. In an era before neonatal intensive care units, before phototherapy lamps, before fetal monitoring, the disease took its toll quietly, family by family, generation by generation. And beneath the grief lay the evolutionary question that haunted the researchers who understood the science. This was not a rare genetic disorder affecting a handful of families. In populations where Rh-negative blood was common, this incompatibility would have affected thousands of pregnancies in every generation. Natural selection should have crushed it. A trait that kills second and third children, the very children who represent a family's deepest investment in reproduction, should have been driven to extinction in a few thousand years. Yet, Rh-negative blood remained. It persisted at 15% globally, at 30% among the Basques, at 25% across the Atlantic fringe of Europe. Something was sustaining it. Something that the grief-stricken families and the overwhelmed obstetricians could not see. An advantage hidden so deeply in the machinery of survival that it would take decades more of research, and a journey backward through human history to even begin to glimpse its outline. But before that journey could begin, the immediate crisis needed a solution. And that solution, when it finally came, would arrive not as a breakthrough of theoretical brilliance, but as a simple injection, given in a quiet moment after birth, that would silence the war inside a mother's body before it ever started. Chapter 4: The Injection That Saved a Generation. 3 men in New York and 1 man in Liverpool, working oceans apart, arrived at the same elegant idea: stop the war before the first shot is fired. The idea was so counterintuitive that when it was first proposed, most of the blood banking community dismissed it outright. The logic ran like this: if the problem was that an Rh-negative mother's immune system learned to attack Rh-positive cells, then the solution was to prevent that learning from ever taking place. And the way to prevent it was, paradoxically, to give the mother the very antibodies she was trying to avoid producing. It sounded like fighting fire with fire, or, more precisely, like vaccinating someone against their own immune response. In Liverpool, England, a physician named Ronald Finn was the first to articulate the concept publicly, around 1960. Finn had been studying the patterns of Rh sensitization in local populations and noticed that women who were already producing anti-Rh antibodies from a previous transfusion were less likely to become sensitized by a subsequent pregnancy. Their existing antibodies seemed to clear the fetal cells before the immune system could mount its own response. Finn proposed that if you injected an Rh-negative mother with a dose of anti-Rh antibodies shortly after she delivered an Rh-positive baby, those borrowed antibodies would coat and destroy any fetal cells that had entered her bloodstream during delivery. The fetal cells would be cleared before her immune system ever noticed them. No recognition, no memory, no sensitization. The next pregnancy could proceed as safely as the first. Nearly simultaneously, across the Atlantic, 3 researchers arrived at the same conclusion through a different path. Vincent Frieda was an obstetrician at Columbia Presbyterian Medical Center in New York. A man who had spent years watching the devastation of Rh disease in his maternity wards and refused to accept it as inevitable. John Gorman was the director of the hospital's blood bank, trained in immunology, with the kind of mind that saw connections between disparate fields. Together, they formed a partnership driven by frustration and hope. The third member of the team was William Pollack, an immunologist and protein chemist working at Ortho Pharmaceutical Corporation in Raritan, New Jersey. Pollack possessed a critical skill that the Columbia team lacked. He knew how to fractionate human plasma, how to isolate specific antibodies from donated blood and concentrate them into a form pure enough for injection. Without Pollack's technical expertise, the idea would have remained theoretical. The skepticism they faced was fierce. The entire blood banking establishment had spent decades teaching doctors that antibodies against blood group antigens were dangerous, that exposure to foreign blood proteins was something to be avoided at all costs. Now these 3 men were proposing to deliberately inject antibodies into healthy women. Colleagues shook their heads. Journal reviewers raised objections. The institutional resistance was thick enough to stop lesser men. Frieda, however, had the full backing of Columbia's obstetrics department, and Pollack had secured financial support from Ortho. They pressed forward. Their first challenge was to prove the concept in a controlled setting, which meant finding volunteers willing to be injected with Rh-positive blood and then treated with the experimental antibody preparation. The volunteers they found were inmates at Sing Sing Correctional Facility in New York, men who agreed to participate in a trial that would have no direct benefit to themselves. The experiments were straightforward in design. The researchers injected Rh-negative male volunteers with small amounts of Rh-positive red blood cells, simulating the fetal cell exposure that occurs during delivery. Some volunteers received the anti-Rh antibody preparation afterward. Others did not. The team then monitored all the volunteers for signs of sensitization. watching to see whose immune systems learned to produce their own anti-Rh antibodies and whose did not. The results were unambiguous. Volunteers who received the antibody injection showed no sensitization. Their immune systems never developed their own anti-Rh response. The borrowed antibodies had done their work quietly, clearing the foreign cells before the immune system could catalog them. Volunteers who did not receive the injection became sensitized at the expected rate, their bodies dutifully producing the very antibodies that, in a pregnant woman, would cross the placenta and attack a future child. Gorman's sister-in-law became the first at-risk woman to receive a prophylactic injection on the last day of January 1964. She was Rh negative, her husband Rh positive, and she had just delivered an Rh positive baby. The injection was given quietly, without ceremony. A small vial of concentrated antibodies slipped into her bloodstream through a needle in her arm. She did not become sensitized. Her subsequent pregnancies were safe. Clinical trials followed, organized by Pollack across 42 medical centers in the United States, Great Britain, Germany, Sweden, Italy, and Australia. The data accumulated with a clarity that is rare in medicine. The treatment worked. It worked reliably, it worked safely, and it worked on a scale that left no room for doubt. The incidence of sensitization among treated mothers dropped from roughly 14% to less than 1%. On the 1st of June, 1968, the United States Food and Drug Administration approved the treatment under the brand name Rogam. The first person to receive the officially approved drug was a woman named Marianne Cummins, 29 years old, pregnant with her third Rh-positive child, living in Teaneck, New Jersey. She had read about the new treatment in the newspaper and realized that her due date, May 27th, would fall just 4 days before the drug became available. She asked her doctor to delay the injection until the approval came through. He agreed. On the day the drug was released, mere hours after it became officially available, Cummins received her injection. Her baby was healthy. Her immune system remained naive to the Rh antigen. She would go on to have more children without complication, a future that would have been unthinkable just a few years earlier. Within a year of the approval, nearly every pregnant Rh-negative woman in the United States, Canada, and most of Europe was receiving the drug. The effect was immediate and dramatic. Deaths from hemolytic disease of the newborn dropped by more than 90% in countries where the treatment became standard care. 10,000 babies a year in the United States alone, who would have died or suffered permanent damage, were now being born healthy. The protocol became routine so quickly that within a generation, most people had forgotten the disease it prevented. Every pregnant woman received a blood type test. If she was Rh negative and her partner was Rh positive or unknown, she received a Rogam injection around 28 weeks of pregnancy and again after delivery. Additional doses followed any event that might cause fetal blood to enter maternal circulation, a miscarriage, an amniocentesis, a fall. The injections were given in clinic rooms and hospital corridors with the same casual efficiency as a flu shot. A few minutes of mild discomfort standing between a mother and a catastrophe she would never know she had avoided. In 1980, Freda, Gorman, Pollack, Finn, and Cyril Clarke, a British geneticist who had contributed to the Liverpool research, shared the Albert Lasker Clinical Medical Research Award, one of the most prestigious honors in American medicine. The award recognized not just the development of a drug, but the rescue of a biological impasse that had plagued humanity for as long as Rh negative and Rh positive humans had been having children together. That impasse had lasted, by rough estimate, tens of thousands of years. Across all those millennia, in every generation, in every population where Rh-negative blood was common, mothers had lost babies to a war they could not see and did not understand. They had blamed spirits, curses, divine punishment, weak constitutions, bad air. They had buried infant after infant in churchyards and village plots, sometimes 6 or 7 from a single family, each grave smaller than the one before. Now a single injection, given at the right moment, could end the cycle. The biochemistry was elegant. The clinical results were overwhelming. The human cost of the centuries before the solution was incalculable. And yet the trait that had caused all that suffering remained. Rh-negative blood did not disappear after Rogam. It persisted. Common as ever, passed from parent to child in the same quiet arithmetic of inheritance that had carried it through the ages. Which meant the deeper question was still unanswered. Not how to prevent the damage, but why the trait existed in the first place, why evolution had allowed it to survive, and why, when you mapped its frequency across the surface of the Earth, the pattern that emerged looked less like a random scattering, and more like a message written in geography, pointing back toward a very specific corner of the world where something ancient and unexplained had left its mark in blood. Chapter 5. The Map That Should Not Exist. When researchers began testing populations around the world, the numbers arranged themselves into a pattern so precise it looked deliberate, as though someone had drawn a border across the human species in invisible ink. Imagine a map spread across a table in a dim room. Not a map of countries or roads, but a map of blood. Each region shaded according to a single question. What percentage of the people living there carry Rh-negative blood? The colors deepen in one corner and fade in all others, and the shape they make is the kind that keeps geneticists awake long after their colleagues have gone home. Start at the epicenter, the Western Pyrenees, where the mountains rise between Spain and France, stone and cloud and silence. Here, among the Basque people, Rh-negative blood reaches its highest concentration anywhere on Earth. Studies have consistently measured phenotypic frequencies between 25 and 35%. And when researchers at the University of the Basque Country sequenced the RHD gene directly, they found the deletion allele present at 47%, the highest figure ever recorded in any population. 1 in 3 Basques, roughly, lacks the Rh protein on their red blood cells. Not a rare anomaly, not a statistical curiosity, a defining characteristic of the population, as much a part of their biological identity as the shape of their faces or the language on their tongues. To find a trait this common in a single group, while it barely exists in others, is to find a question that demands an answer. Move west from the Basque Country into the rest of the Iberian Peninsula. The frequency drops, but not by much. Portugal and central Spain show Rh-negative rates around 20 to 25%, still far above the global average. The Atlantic coast holds onto its numbers, like a cliff holds onto its rock, resistant to erosion, slow to change. Cross the water to Ireland, and the frequency stays elevated. The Irish, particularly in the rural West, carry Rh-negative blood at rates around 25%. Scotland follows a similar pattern, especially in the Highlands and the Islands, where isolation preserved old genetic profiles long after lowland populations had mixed with newcomers from the south and east. Wales, Cornwall, Brittany in northwestern France, all the Celtic regions, all the Atlantic fringe, all showing the same stubborn elevation. Now turn east. Cross the English Channel into the heart of continental Europe and watch the numbers begin to fall. France as a whole averages around 16%. Germany sits near 15%. Poland is similar. Continue east into Russia and the frequency drops further, to 8 or 10% in some regions. The gradient is smooth, steady, almost mathematical, as though someone had tilted the continent and let the Rh-negative trait flow slowly toward the western edge, pooling where it met the sea. Head south into the Mediterranean basin, and the picture shifts again. Greece and southern Italy show moderate frequencies, around 15 to 18%, consistent with their position as crossroads where many populations have met and mingled over thousands of years. But travel further east, into Turkey, and the numbers fall. Into the Middle East, lower still. By the time you reach the Indian subcontinent, Rh-negative frequencies dip below 5% in most indigenous communities. East Asia tells an even starker story. Japan registers less than 1%. China is similar. Korea, Southeast Asia, the islands of the Pacific, all show Rh-negative blood at frequencies so low that when it appears, researchers must consider whether it arrived through recent European admixture rather than ancient inheritance. The trait that defines nearly a third of the Basque population is virtually absent from billions of people on the other side of the world. Africa presents perhaps the most dramatic contrast of all. In most sub-Saharan populations, Rh-negative blood is extraordinarily rare, often measured below 1%, sometimes registering as a fraction, so small it rounds to zero. The continent where humanity was born, where our species spent hundreds of thousands of years evolving before spreading across the globe, shows almost no trace of the trait that clusters so densely in one corner of Western Europe. The Americas before Columbus tell the same story. Among indigenous populations with no European ancestry, Rh-negative blood was effectively non-existent. The trait that appears in the Western Hemisphere today arrived with European colonizers, mixing into populations that had never carried it. Pre-Columbian bloodlines were almost exclusively Rh-positive, as though the entire New World had been populated by people who carried the protein without exception. Stand back from the map, and the pattern is unmistakable. A single peak in Western Europe, highest in the Pyrenees and the Atlantic fringe. A smooth gradient declining toward the east, near absence everywhere else. This is not the distribution of a random mutation drifting through humanity at large. This is the distribution of something specific, something rooted in a particular place and time, preserved in populations that remained isolated while the rest of the world moved on. The conventional explanation assembles the pieces into a coherent story. Around 5,000 years ago, waves of migration swept westward across Europe from the Pontic steppe, north of the Black Sea. These were the Indo-European-speaking peoples, carrying bronze tools, domesticated horses, and a genetic profile that would reshape the continent. As they moved west, they mixed with the populations already living there, populations that had inhabited Europe for tens of thousands of years. In the east, where the migrants originated, their genes dominate. In the west, where they arrived later and in smaller numbers, the older genetic patterns survived in greater proportion. The Atlantic populations, the Basques and Irish and Highland Scots, were the least affected by these eastern migrations. They retained more of the ancient European genetic heritage, the heritage that included high frequencies of Rh-negative blood. The gradient on the map, in this reading, is simply the record of incomplete mixing. Old blood and new blood blended unevenly across the continent, the proportions determined by geography, timing, and the stubborn resistance of mountain and ocean to the movement of peoples. The Basques did not develop Rh-negative blood. They preserved it, holding on to a pattern that once may have been common across a much wider territory. But this explanation, tidy as it is, leaves the central question untouched. Why was this particular trait so common in those ancient European populations in the first place? Genetic mutations happen constantly, but they do not usually reach 30 or 40% frequency without a reason. Natural selection should have kept Rh-negative blood rare, punished by the pregnancy complications it caused, slowly winnowed down to a footnote in the genetic record. Instead, it thrived, climbed to extraordinary levels, and held its ground for millennia. Some researchers have pointed to the Berber populations of North Africa, in the mountains of Morocco and Algeria, where Rh-negative frequencies also rise above the surrounding average. The Berbers, like the Basques, speak a language that stands apart from the dominant family of their region. They carry genetic markers suggesting deep roots in North Africa, predating the Arab expansion by thousands of years. Mountains protect, mountains isolate, and in the protected places, old patterns survive. The map, then, is not just a map of where Rh-negative blood exists today. It is a map of where ancient populations managed to resist the genetic tides that reshaped the rest of Eurasia. It is a map of survival, of isolation, of stubborn continuity in the face of change. And somewhere in the oldest corners of that map, in the stone villages and high pastures of the Pyrenees, the story of why this blood exists at all is still being told in a language that almost no one else on Earth can understand. Chapter 6: The Last Language and the Oldest Blood. In the mountains between Spain and France, a people who should not exist by every rule of cultural absorption continue to speak a language that belongs to no family, and carry blood that belongs to no easy explanation. The road into the Basque Country climbs through green valleys where sheep graze on slopes so steep the animals seem to defy gravity. Stone farmhouses sit low against the hills, their walls thick enough to hold back winter, their roofs dark with lichen and rain. Smoke rises from chimneys in the morning, thin and pale, against a sky that changes color 3 times before noon. This is not a landscape that invites conquest. It is a landscape that absorbs it, swallows armies and ambitions into its folds, and continues as it was. The people who live here call themselves Euskaldunak, the speakers of Euskara. Their language is the oldest surviving thread of spoken identity in Europe, a tongue so ancient and so isolated that linguists have spent more than a century trying to connect it to something else, and have failed. It is not Spanish. It is not French. It is not related to any Indo-European language, the vast family that includes English, Russian, Hindi, Greek, and nearly every other tongue spoken from Ireland to India. Euskara stands alone, a linguistic island in a continent of related languages, as though everyone around the Basques adopted new words and new grammars over the millennia, while the Basques simply kept speaking what they had always spoken. Scholars have compared it to Caucasian languages, to ancient Iberian inscriptions, to Berber dialects across the Mediterranean, to languages from every corner of the ancient world. Nothing fits. Every proposed connection has dissolved under closer examination, leaving Euskara where it began, unclassified and unexplained. The verbs in Euskara are extraordinarily complex. A single verb form can encode the subject, the direct object, the indirect object, and the tense, all within a single word built from layers of prefixes and suffixes. The counting system is vigesimal, based on 20 rather than 10, a pattern found in only a handful of languages worldwide. Even the most basic vocabulary shares almost nothing with the languages that surround it. The word for house is exi. The word for water is The word for stone is hari. None of these resemble their Spanish or French equivalents. This linguistic isolation is not an accident of geography alone. Languages disappear when their speakers are absorbed, conquered, converted, or displaced. Across Europe, the Indo-European expansion wiped out nearly every indigenous tongue in its path. Languages that had been spoken for thousands of years vanished within generations, replaced by the speech of newcomers who brought agriculture, bronze, and eventually iron. Only Euskara survived, sheltered by mountains and sustained by a people who refused to become someone else. The genetic evidence tells a parallel story. When population geneticists first began analyzing Basque DNA in the late 20th century, they found a profile that confirmed what the language had suggested. The Basques carried markers that placed them among the most genetically ancient populations in Europe, with less admixture from the Neolithic farming migrations and the later Bronze Age steppe migrations than almost any other European group. They were not completely isolated. No human population ever is. Trade, intermarriage at the margins, occasional warfare, all left traces in the Basque genome. But the core of their genetic identity remained remarkably stable. A reservoir of ancient European variation preserved through millennia of change. And among the traits preserved most strikingly was the frequency of the RhD gene deletion, the genetic signature of Rh-negative blood. The connection between language and blood type is not causal. Speaking Euskara does not make your blood Rh-negative, but both traits are markers of the same underlying phenomenon: deep isolation and continuity. The Basques preserved their language because they preserved their community. They preserved their community because the mountains protected them. And in that protected space, genetic patterns that had once been common across a much wider territory survived, concentrated, undiluted by the waves of migration that reshaped the rest of the continent. During the last glacial maximum, roughly 20,000 years ago, much of northern Europe lay under ice. Glaciers covered Scandinavia, Britain, and the northern plains of the continent. Human populations retreated to a handful of refugia, pockets of habitable land where small bands could survive the cold. The Franco-Cantabrian region, the strip of territory along the northern coast of Spain and southern coast of France that includes the Basque Country, was one of the most important of these refugia. Here, in valleys sheltered from the worst of the glacial winds, small groups of hunter-gatherers held on. They hunted red deer and wild horse across tundra-like grasslands. They gathered shellfish along the coast. They painted extraordinary images on the walls of caves, at Altamira, at Lascaux, at Chauvet, leaving behind evidence of a rich symbolic life sustained through conditions that would test any population to its limits. These were the Cro-Magnons, the first anatomically modern humans in Europe, who had arrived on the continent perhaps 45,000 years ago. They were not Neanderthals. The Neanderthals had been in Europe for over 200,000 years before them, adapted to the cold, powerfully built, carrying their own culture and their own genetic heritage. The two species coexisted for thousands of years, and we know now from ancient DNA that they sometimes interbred. Modern Europeans carry between 1% and 4% Neanderthal DNA, a legacy of encounters that took place across millennia of shared territory. Some researchers have wondered whether the Rh-negative trait might be one of the genetic legacies of that long coexistence, a variant that emerged in early European populations either through Neanderthal admixture or through the unique selective pressures of life in glacial Europe. The evidence is circumstantial, and no direct link between Neanderthal DNA and the RHD deletion has been established. But the geographic overlap is suggestive. The regions where Rh-negative blood reaches its highest frequencies are the same regions where the oldest continuous human habitation in Europe is documented. When the glaciers retreated beginning around 15,000 years ago, human populations expanded out of the southern refugia and recolonized the newly habitable north. The Basque ancestors were part of that expansion, carrying their language, their culture, and their genetics into a world that was rapidly transforming. Forests replaced tundra. Rivers swelled. New animals arrived, and the old hunting patterns gave way to new ones. Then came the Neolithic Revolution. Beginning around 8,000 years ago, farming communities from the Near East began spreading westward across Europe, bringing wheat, barley, cattle, and sheep. They also brought their own genetic profiles, which gradually mixed with those of the existing hunter-gatherer populations. In most of Europe, this mixing was extensive. The genetic signature of the Neolithic farmers dominates the genome of most modern Europeans. But in the Basque Country, the mixing was minimal. The mountains acted as a barrier, slowing the advance of farming communities and limiting genetic exchange. The Basques adopted some agricultural practices over time, but they did not absorb the farming populations the way their neighbors did. Their genetic profile remained closer to the pre-Neolithic pattern, preserving high frequencies of traits that had been diluted elsewhere. A similar story played out along the Atlantic coast. Ireland, Western Scotland, Wales, Brittany, all regions where Rh-negative blood remains elevated. All regions that were geographically peripheral to the main routes of Neolithic and Bronze Age expansion. These populations received less genetic input from the incoming waves, and therefore retained more of the older patterns. They are not identical to the Basques, but they share the same dynamic, isolation-preserving antiquity. The Berber populations of North Africa add another layer to the picture. In the Rif Mountains of Morocco and the Kabylia region of Algeria, Rh-negative frequencies rise to 15 or 20%, higher than the surrounding Arab-speaking populations. The Berbers, like the Basques, are mountain people with an ancient linguistic tradition and a genetic profile that suggests deep roots predating later migrations. Some genetic studies have found distant but real connections between Basque and Berber populations, not recent mixing, but deep shared markers suggesting that both groups preserve elements of populations that once inhabited a larger territory around the Western Mediterranean. The pattern, then, is not a mystery without any answer. It is a mystery with a partial answer and many remaining questions. The partial answer is demographic. Rh-negative blood was probably common in the ancient populations of Western Europe and northwestern Africa before the great migrations of the Neolithic and Bronze Age. Those migrations diluted the trait across most of the continent, but in the places where geography provided protection, the old frequencies survived. The remaining questions are harder. Why was the trait common in those ancient populations? What advantage, if any, did it provide to hunter-gatherers living in glacial Europe? Was it favored by natural selection, maintained by genetic drift in small, isolated groups, or sustained by some mechanism that researchers have not yet identified? The Basques carry the answer in their blood, but they have not yet been persuaded to give it up. In the villages of the Basque Country, evening falls early in winter. The mountains cut the light, and the valleys fill with shadow long before the sky goes dark. Families gather in stone kitchens where the walls are thick and the fire burns low. Somewhere outside, a dog barks once and falls silent. The language spoken around the table tonight was spoken around tables in these same valleys 10,000 years ago, and 20,000, and perhaps longer than that. The blood that moves through the hands, holding the bread and the wine, is blood that has traveled from the deep past, carrying a story that the speakers do not need to tell because they are still living it, word by word, generation by generation, heartbeat by heartbeat, in the last place on earth where the oldest thread of European identity has never been cut. Chapter 7. When Crowns Carried Curses. For centuries, the royal families of Europe believed their blood was sacred. They were right that it was different. They were wrong about why. And the price of their mistake was written in the graves of children and the fall of empires. The phrase blue blood did not begin as a metaphor. In medieval Castile, the pale-skinned Christian nobility held up their wrists and pointed to the veins visible beneath their skin. Blue-green lines tracing paths toward the heart. The color, they said, proved their lineage had not been mixed with that of the darker-skinned Moors, who had ruled much of the Iberian Peninsula for centuries. Sangre azul. Blue blood. Proof of purity, worn beneath the skin like a seal stamped by God. It was a small vanity, rooted in sunlight and pigmentation, but it grew into something larger. Across Europe, royal and aristocratic families became obsessed with the purity of their bloodlines. Marriage was not a matter of love or even alliance alone. It was a genetic transaction, conducted with the care of a horse breeder selecting stock, designed to keep certain qualities in and certain others out. Cousins married cousins. Uncles married nieces. The family trees of European royalty stopped being trees and became something more like wreaths, loops folding back on themselves, generation after generation. The logic was ancient and intuitive. If your blood was noble, if it carried something that set you apart from common people, then mixing it with common blood would dilute the gift. Better to marry within the family, within the circle of proven lineage, and keep the precious substance undiluted. They did not know about genes. They did not know about recessive traits or inbreeding coefficients. They only knew that blood mattered, and they were determined to keep theirs pure. The consequences arrived slowly, then all at once. Consider the Spanish Habsburgs, who ruled from 1516 to 1700 and practiced consanguineous marriage with a devotion that bordered on religious fervor. Philip I, the founder of the dynasty, had an inbreeding coefficient of 0.025, a modest figure reflecting the ordinary degree of relatedness among European nobility at the time. 5 generations later, his descendant Charles II carried a coefficient of 0.254. To understand what that number means, consider that the expected coefficient for the child of 2 siblings is 0.25. Charles II, born of an uncle-niece marriage between Philip IV and Mariana of Austria, was more inbred than if his parents had been brother and sister. This was not because of a single disastrous union, but because of the accumulated weight of generations. Each marriage adding another loop to the wreath, each generation concentrating recessive alleles that in a more diverse population would have remained safely hidden. The portraits tell the story that the court physicians were too discreet to write. Diego Velázquez, the greatest painter in Spain, rendered the Habsburg features with the unflinching honesty that was his genius. The protruding lower jaw, the mandibular prognathism that became known as the Habsburg jaw, grows more pronounced from canvas to canvas as the generations progress. Charles I shows a noticeable underbite. Philip IV's jaw extends further. By the time Velázquez's successor Juan Carreño de Miranda painted Charles II, the jaw had become a deformity. Charles could not chew his food. His teeth did not align. His tongue was so large that he had difficulty speaking, and those who heard him described his words as thick and difficult to understand. He was reportedly unable to walk until he was nearly fully grown, his legs too weak to support his body. He suffered from seizures. Historical accounts describe him as intellectually impaired, unable to manage the basic functions of governance. A king in name, presided over by regents and advisors who ran the empire in his stead. He was called El Hechizado, the bewitched. His subjects believed he was cursed, that some malevolent force had twisted his body and clouded his mind. In a sense, they were right, though the curse was not supernatural. It was genetic. Modern analysis suggests that Charles II likely suffered from at least two distinct genetic disorders: combined pituitary hormone deficiency and distal renal tubular acidosis, both caused by recessive alleles that had been concentrated through generations of inbreeding until they could no longer be masked. Charles died in 1700 at the age of 38. He had no children. His two marriages produced no heirs. His infertility, almost certainly another consequence of his genetic burden, ended the Spanish Habsburg line and triggered the War of the Spanish Succession, a conflict that engulfed Europe for 13 years and killed hundreds of thousands of soldiers and civilians across the continent. A dynasty that had spent 2 centuries trying to preserve the purity of its blood was destroyed by that very purity, brought down not by enemies at the gate, but by enemies in the chromosomes. 2 centuries later, another royal family would learn a different but equally devastating lesson about the secrets hidden in blood. Queen Victoria of England, born in 1819, ascended to the throne at 18 and ruled for 63 years, presiding over an empire that spanned a quarter of the globe. She had 9 children and married them strategically into every major royal house in Europe, weaving a web of dynastic connections that earned her the title Grandmother of Europe. Victoria was also, unknowingly, a carrier of hemophilia B, a rare and severe form of the bleeding disorder caused by a mutation on the X chromosome. The mutation was probably spontaneous, arising in Victoria herself, or possibly in her father, rather than inherited from earlier generations. She showed no symptoms, as women who carry a single copy of the mutant gene are typically protected by the normal copy on their other X chromosome. But her sons had a 50% chance of inheriting the disease, and her daughters had a 50% chance of becoming carriers. Her youngest son, Leopold, Duke of Albany, was the first to show symptoms. From early childhood, he bruised easily, bled excessively from minor injuries, and suffered episodes of internal bleeding that left him in agony for days. Hemophilia in the 19th century was a sentence of constant vigilance. There was no treatment, no clotting factor replacement, no understanding of the molecular machinery that had gone wrong. Leopold lived with the knowledge that a stumble, a bump, a fall on a staircase could kill him. On the 27th of March, 1884, in Cannes, France, Leopold slipped and fell. He struck his knee and hit his head. For a person with normal blood, the injuries would have been trivial. For Leopold, they triggered a cerebral hemorrhage that his body could not stop. He died the following morning. He was 30 years old. Victoria's 2 carrier daughters, Alice and Beatrice, married into the royal houses of Germany and Spain, carrying the hemophilia gene with them, like a lit fuse threaded through the genealogical map of Europe. Alice's daughter Alex became Empress Alexandra of Russia, wife of Tsar Nicholas II. Beatrice's daughter Victoria Eugenie became Queen of Spain, wife of Alfonso XIII. In both families, the bleeding disease appeared in the next generation, striking sons with a randomness that felt to their parents like divine cruelty. In Russia, the consequences reached beyond medicine into history. Alexandra gave birth to Alexei, the heir to the throne, in 1904. The boy was hemophilic. From infancy, every bump and bruise became a crisis, every nosebleed a potential emergency. Alexandra, devout and desperate, searched for anyone who could ease her son's suffering. She found Grigory Rasputin. Rasputin was a Siberian peasant who had refashioned himself as a holy man, a wandering mystic who claimed the power to heal through prayer and the force of his presence. Whether his abilities were genuine, psychological, or simply the result of keeping doctors and their aspirin away from a boy whose blood could not clot, the effect on Alexei was real enough to convince his mother. Rasputin could calm the boy. The bleeding seemed to ease when he was near. Alexandra clung to this miracle with a faith that would not be shaken. As Russia stumbled through the First World War, Rasputin's influence over the imperial family became a scandal that corroded the monarchy's last reserves of public trust. Nicholas left the capital to command the army at the front. Alexandra, guided by Rasputin, made decisions about government appointments and policy that horrified the aristocracy and infuriated the public. A peasant mystic, whispering in the ear of an empress, while soldiers died by the millions in the trenches. The symbolism was devastating. On the 30th of December, 1916, a group of Russian nobles lured Rasputin to a palace in St. Petersburg and murdered him. The details of his death became legend, embellished with each retelling poison and gunshots and a body thrown into a freezing river. But the murder changed nothing. The damage was done. Less than 3 months later, revolution swept through Russia. Nicholas abdicated. The imperial family was imprisoned. On the night of the 17th of July, 1918, in a basement room in the city of Yekaterinburg, the entire family was executed by Bolshevik firing squad. Nicholas, Alexandra, their 4 daughters, and Alexei, who was 13 years old and still carried in his blood the gene that had brought Rasputin into their lives and helped bring the dynasty to its end. DNA analysis of their remains, conducted decades later, confirmed that Alexei had hemophilia B and that Alexandra and at least 1 daughter were carriers. The hemophilia did not cause the Russian Revolution. The social, economic, and political forces that destroyed the Romanov dynasty were far too vast and too deep to be attributed to a single genetic mutation. But hemophilia shaped the path the destruction took. It brought Rasputin into the inner circle. It isolated the imperial family from the people they ruled. It gave revolutionaries a perfect symbol of royal decadence, a dynasty so consumed by its own fragility that it entrusted the fate of an empire to a faith healer while the empire burned. The lesson hidden in these royal catastrophes is not that blood type determines destiny. It is simpler and sadder than that. The families that spent centuries trying to keep their blood pure were conducting, without knowing it, experiments in the mathematics of genetic isolation. Small populations, restricted breeding pools, generation after generation of the same alleles combining and recombining. The same mathematics that governed the ancient bottlenecks of human prehistory played out in palaces instead of caves, with crowns instead of stone tools, but following the same inexorable rules. Diversity is not a luxury. It is the mechanism by which populations absorb harmful mutations, buffer against disease, and maintain the flexibility to adapt. The Habsburgs learned this through extinction. The Romanovs learned it through revolution. The lesson was written in their blood, but they could not read it, because the science that would have explained it had not yet been born. Chapter 8. Theories at the Edge of Science. When mainstream explanations leave gaps, the human mind fills them with stories. Some of those stories are plausible. Some are extraordinary, and a few sit precisely on the border where science has not yet decided which is which. In a laboratory in Leipzig, Germany, a technician lowers a fragment of ancient bone into a solution designed to dissolve everything except the DNA preserved inside. The bone is 40,000 years old, recovered from a cave in Croatia, where Neanderthals once sheltered from the cold. The technician works in a sealed room with filtered air, wearing a full bodysuit to prevent contamination from her own cells. A single flake of modern skin, a stray eyelash, a cough, could ruin months of careful preparation. This is the world of ancient DNA research, a discipline that barely existed a generation ago, and now routinely extracts genetic information from remains that have lain in the earth for tens of thousands of years. The technology has transformed our understanding of human evolution, revealing connections and separations that fossils alone could never show. And it is through this technology that the most scientifically grounded hypothesis about the origins of Rh-negative blood has begun to take shape. The hypothesis begins with the Cro-Magnons, the first anatomically modern humans to enter Europe roughly 45,000 years ago. These were not Neanderthals. The Neanderthals had been living in Europe for over 200,000 years, perfectly adapted to the cold, powerfully built, carrying their own cultures and genetic heritage. The newcomers were different, taller, lighter-boned, carrying with them the tools of the Upper Paleolithic, art, symbolic thought, and technologies that would eventually displace their older cousins. We know now that the two species interbred. Ancient DNA analysis has proven this beyond question. Modern Europeans carry between 1 and 4% Neanderthal DNA, traces of encounters that occurred across thousands of years of shared territory. The mixing was not constant or uniform. It happened in specific times and places, most likely between 47,000 and 65,000 years ago. And the genes that survived in modern populations are not randomly distributed. Some Neanderthal alleles were beneficial and were retained by natural selection. Others were harmful and were gradually purged. Some researchers have wondered whether the RHD gene deletion, the genetic change that produces Rh-negative blood, might be connected to this ancient interbreeding, not necessarily inherited directly from Neanderthals, but arising in the unique genetic environment created by the mixing of two distinct human lineages. The evidence is circumstantial. No Neanderthal genome sequenced so far has revealed the specific RHD deletion found in modern Rh-negative individuals. But the geographic overlap between the highest Rh-negative frequencies and the regions of longest continuous modern human habitation in Europe is suggestive. A more cautious version of the hypothesis sidesteps the Neanderthal question entirely and focuses on the selective pressures of Ice Age Europe. Small populations, living in glacial refugia like the Franco-Cantabrian region, would have experienced intense genetic drift, the random fluctuation of allele frequencies that becomes powerful when population sizes are small. In a band of a few hundred individuals, a neutral or mildly beneficial mutation can rise to high frequency within a few dozen generations simply by chance. If the RHD deletion arose in one such small population, perhaps in the Pyrenean refugium during the last glacial maximum. It could have reached 30 or 40% frequency before the glaciers retreated and populations began to expand. Once established at that level, it would have been difficult to eliminate entirely, even if it carried reproductive costs. The mathematics of population genetics predict that a trait maintained at high frequency in a founding population will persist for thousands of generations even under mild negative selection, declining slowly like a river that takes centuries to change its course. This is the mainstream explanation, and it has the virtue of parsimony. It requires no exotic mechanisms, no outside intervention, no lost civilizations. Just the ordinary machinery of mutation, drift, and population structure operating over deep time. Most population geneticists accept some version of this account, though they acknowledge that the details remain incomplete and that the question of selective advantage has not been fully resolved. But the mainstream explanation has never been the only one. From the moment the Rh factor was identified, the trait attracted speculation that ranged from the cautiously heterodox to the frankly extraordinary. Some of these theories have been proposed by credentialed researchers working at the edges of their disciplines. Others have emerged from popular culture, amplified by the internet, and taken on lives of their own in forums and late-night conversations. They deserve to be mentioned, not because they are equally supported by evidence, but because they illuminate the human need to find meaning in the mysterious. The Atlantis hypothesis connects Rh-negative blood to the legendary civilization described by Plato, supposedly destroyed by a catastrophe around 11,000 years ago. If survivors of that destruction dispersed to nearby lands, the theory goes they might have settled in regions that now show elevated Rh-negative frequencies. The Basque Country, Ireland, parts of North Africa. The Rh-negative trait in this reading is a genetic remnant of a lost advanced society preserved in the populations that absorbed its refugees. There is no archaeological evidence for any of this. No sunken cities with advanced technology have been found. No genetic markers can be traced to a single catastrophic diaspora 11,000 years ago. Plato's account of Atlantis, composed in the 4th century before the Common Era, is widely regarded by historians as philosophical allegory rather than historical reportage. The theory persists not because of its evidentiary strength, but because it offers a narrative that makes Rh-negative blood feel connected to something grander than random mutation. Further from the mainstream lies the ancient astronaut hypothesis. The premise is straightforward. At some point in human prehistory, extraterrestrial beings visited Earth and interbred with humans. The offspring of these unions carried genetic markers that distinguish them from purely terrestrial humans, and Rh-negative blood is one of those markers. Proponents cite ancient texts describing gods descending from the sky, artwork that appears to show figures in technological apparatus, and the unusual properties of Rh-negative blood itself, particularly the pregnancy complications, as evidence that the trait was introduced from outside the human lineage. Mainstream science dismisses this hypothesis entirely. The pregnancy complications associated with Rh incompatibility can be explained through standard immunological mechanisms. The geographic distribution of Rh-negative blood matches population genetics models, and the extraordinary claim that extraterrestrial beings interbred with humans requires extraordinary evidence, of which none has been produced. The biblical interpretation draws on a different tradition. The book of Genesis mentions the Nephilim, described as the offspring of the sons of God, and the daughters of men. The text is brief, cryptic, and has been interpreted in countless ways over the centuries. Some writers have connected the Nephilim to ancient royal bloodlines, to the divine right of kings, and ultimately to the Rh-negative trait, suggesting that the blood type preserves the genetic legacy of a lineage that was, in some sense, more than ordinarily human. The text itself does not support these connections. The passage about the Nephilim occupies a few verses in Genesis and provides almost no detail about who they were, what they looked like, or what became of them. Connecting a specific blood group antigen to a passage of ancient scripture requires assumptions that the scripture does not authorize. Yet the appeal is understandable. For people searching for explanations of why they feel different, why their blood type is rare, why their bodies seem to respond to the world in unusual ways, a sacred lineage offers something that a random mutation cannot: significance. What all these theories share, from the cautiously scientific to the frankly speculative, is a dissatisfaction with randomness. The idea that 15% of humanity carries a blood type that creates dangerous pregnancy complications, that clusters in specific populations, and that defies easy evolutionary explanation, all because of an accident, an arbitrary deletion in a gene, a roll of the genetic dice, feels insufficient to many people. They want a reason, a story, a why. Science is honest enough to admit that it does not yet have a complete why. The mainstream explanation accounts for the mechanics of how Rh-negative blood arose and spread. But the question of selective advantage remains open. A few studies have suggested that Rh-negative individuals might show subtly different immune responses, possible resistance to certain parasites, slightly different reactions to specific infections. But the evidence is preliminary, inconsistent, and far from the kind of clean, decisive finding that closes a question for good. In the gap between what science knows and what it does not, the theories flourish. They will continue to flourish as long as the gap remains open. And perhaps that is not entirely a bad thing. As long as the boundary between evidence and speculation is clearly marked, because the impulse to look at a mystery and refuse to accept that it is simply random, that there must be a reason, that the story must mean something, is the same impulse that drives the best science. It is the impulse that led Landsteiner to his microscope, Levine to his serum tests, and Frieda and Gorman to their improbable injection. The difference between good science and appealing mythology is not in the questions they ask. It is in the discipline with which they test the answers. And the answers, for Rh-negative blood, are still being tested in laboratories where ancient bones surrender their secrets one fragment at a time, and in population studies that grow larger and more detailed with every passing year. The truth, when it finally arrives, may be simpler than the exotic theories and more complex than the standard mutation account. Human genetics is messy. Our history is complicated. And sometimes the most interesting answers are the ones that require us to hold uncertainty in one hand and curiosity in the other, walking forward without knowing exactly where the path leads, trusting that the questions themselves are worth the journey. Chapter 9: The Evolutionary Paradox. A trait that kills babies should not survive. A trait that reaches 30% in any population should have a reason. Between those two facts lies a contradiction that evolution has refused, for tens of thousands of years, to resolve. In a laboratory at Charles University in Prague, a parasitologist named Jaroslav Fleger sat in front of a computer screen watching numbers that did not make sense. It was the mid-2000s, and Fleger had spent years studying Toxoplasma gondii, a single-celled parasite carried by cats that infects roughly a third of the world's human population. Most people never know they carry it. The parasite settles quietly into muscle and brain tissue, forming tiny cysts that the immune system walls off but never fully destroys. A silent passenger, riding for decades in the bodies of hosts who feel nothing. Except that Fleger had been finding that infected people did feel something, or rather, that they behaved differently from uninfected people in ways so subtle that only careful testing could detect them. Infected men showed slightly slower reaction times, slightly higher risk-taking behavior. Infected women showed different patterns. The differences were small, contested, difficult to replicate. Exactly the kind of findings that make epidemiologists cautious and journalists excited. But it was when Fleger began sorting his data by Rh blood type that the numbers became truly strange. Among people who were not infected with Toxoplasma, Rh-negative men showed faster reaction times than Rh-positive men. The difference was modest but consistent across multiple studies. Something about lacking the Rh protein on your red blood cells seemed to correlate with a slight cognitive advantage, at least in the narrow domain of psychomotor speed. Among infected individuals, the pattern reversed. Rh-positive heterozygotes, people who carried one copy of the Rhd gene and one copy of the deletion, seemed to be protected against the reaction time impairment caused by the parasite. Their performance stayed stable even when they carried Toxoplasma. Rh-negative individuals and Rh-positive homozygotes both showed the expected slowing. But the heterozygotes, the people with one of each, sailed through unaffected. If this finding held up, it offered something extraordinary, a possible mechanism for heterozygote advantage. In population genetics, heterozygote advantage is the gold standard explanation for why a harmful recessive trait persists at high frequency. The classic example is sickle cell anemia and malaria. Carrying two copies of the sickle cell allele causes devastating disease. Carrying 0 copies leaves you vulnerable to malaria. But carrying one copy of each, being heterozygous, protects against malaria without causing sickle cell disease. The advantage of the middle position keeps both alleles circulating in the population indefinitely. Fleger proposed that something similar might be happening with the Rh blood group and Toxoplasma. In regions where Toxoplasma infection was common, which includes much of Europe, the advantage of being heterozygous for the Rhd deletion could offset the reproductive cost of Rh incompatibility. Heterozygous individuals, carrying one functional Rhd gene and one deleted copy, would be protected against the parasite's effects on cognition and behavior. Meanwhile, the Rh-negative homozygotes would pay the pregnancy cost, and the Rh-positive homozygotes would pay the parasite cost. The heterozygotes, sitting in the middle, would quietly outperform both. The theory was elegant. The data were suggestive, but the scientific community received it with the caution that Fleger's work always attracted, a mixture of intrigue and skepticism. The studies were relatively small. The effect sizes were modest. Reaction time is a noisy measure, influenced by fatigue, attention, motivation, and a dozen other variables that are difficult to control in human subjects. Replication proved inconsistent. Some studies supported Fleger's findings. Others found weaker effects or no effects at all. Still, the hypothesis opened a door that had been closed for decades. For the first time, researchers had a plausible candidate for the selective advantage of Rh-negative blood, not in Rh-negative individuals themselves, but in the heterozygotes who carried the deletion on one chromosome and the functional gene on the other. If heterozygote advantage was driving the persistence of the RHD deletion, it would explain why the trait remained common without requiring it to benefit the people who actually expressed it. The toxoplasma hypothesis was not the only candidate. Other researchers had explored different paths, searching for the hidden benefit that might justify the evolutionary persistence of a trait with such obvious costs. Some had looked at disease resistance more broadly. A few small studies suggested that Rh-negative individuals might show slightly different susceptibility patterns to certain infections, though the results were never clean enough to build a definitive case. The malaria hypothesis, modeled on the sickle cell analogy, attracted attention for a time. If Rh-negative blood provided even modest protection against Plasmodium falciparum, the deadliest malaria parasite, the selective advantage in endemic regions could be significant. But the geographic distribution argued against it. Malaria is most prevalent in sub-Saharan Africa and tropical Asia, precisely the regions where Rh-negative blood is rarest. If the trait protected against malaria, you would expect it to be common in malaria zones, not in the relatively malaria-free mountains of the Pyrenees. Then came the pandemic of 2020, and researchers turned once again to the old question of whether blood type influences susceptibility to infectious disease. Early studies from China and Europe suggested that people with blood type A might face a slightly higher risk of severe illness from the novel coronavirus, while people with type O might face a slightly lower risk. As for the Rh factor, several analyses found that being Rh-negative was associated with a modest reduction in the risk of infection or severe disease. A large study from the Intermountain Healthcare System in the United States, analyzing data from over 180,000 people tested for the virus between March 2020 and May 2021, found that Rh-positive individuals had a statistically higher risk of both infection and severe outcomes. A Canadian population cohort study reported similar findings, with blood type O and Rh-negative status appearing protective against both infection and severity. But as more data accumulated and researchers controlled for confounding variables, age, obesity, chronic illness, access to healthcare, vaccination status, the picture grew murkier. Some studies confirmed the association. Others found it weaker or absent. The consensus by late 2021 was cautious. There might be small correlations between blood type and susceptibility to this particular virus, but the effects were minor compared to the major risk factors, and no one was prepared to claim that Rh-negative blood conferred meaningful immunity. Yet from the perspective of deep evolutionary time, even small effects can matter. A fraction of a % advantage, multiplied across millions of people and hundreds of generations, can shift allele frequencies in ways that are invisible in any single lifetime, but profound over millennia. If Rh-negative heterozygotes enjoyed even a tiny edge against certain common infections, parasites, or environmental stresses, that edge could have been sufficient to maintain the deletion allele in the population, despite the reproductive cost of Rh incompatibility. The honest answer, the one that most researchers give when pressed, is that we do not yet know the full reason why Rh-negative blood persists. The mainstream tools of population genetics can model how it might have risen to high frequency through drift in small populations and been maintained through heterozygote advantage. But the specific selective pressure, the particular environmental challenge that made the RHD deletion worth keeping, has not been conclusively identified. Perhaps it was toxoplasma. Perhaps it was some other pathogen, now vanished or evolved beyond recognition. Perhaps it was a combination of factors, each contributing a small advantage that individually would have been undetectable, but collectively was enough to tip the balance. Or perhaps the answer is simpler and less satisfying. Perhaps there was no grand advantage at all. Perhaps Rh-negative blood is simply a neutral variant that happened to become common in certain isolated populations through the blind arithmetic of genetic drift, and the pregnancy complications it causes were never quite severe enough to eliminate it entirely. Evolution does not always optimize. It tinkers, it improvises, it leaves behind half-finished experiments and redundant machinery. Not every trait that persists has a purpose. Some persist because the cost of eliminating them is not quite high enough to overcome the inertia of inheritance. The human genome is littered with such relics, traits that neither help nor harm enough to be decisively acted upon by selection, drifting through the generations like flotsam on a slow river. But the researchers keep looking. New studies appear every year, using larger datasets, finer genetic tools, and more sophisticated statistical methods. Ancient DNA analysis pushes further back into time, revealing the Rh status of individuals who lived thousands of years ago, and tracing the trajectory of the deletion allele across prehistoric populations. The answer may arrive gradually, not as a single dramatic revelation, but as a slow accumulation of evidence that eventually tips the balance from uncertainty to understanding. Until then, the paradox remains. A trait that should have been eliminated persists. A mutation that causes mothers to attack their own children continues to circulate through the human species, concentrated in certain populations, absent from others, following patterns that whisper of ancient pressures and forgotten advantages. The blood remembers something that the mind has not yet figured out, and the silence of that memory is, in its own way, as eloquent as any answer. Chapter 10. Blood as Identity. It began with a protein on a red blood cell. It became a personality type, a cosmic lineage, a secret club. The journey from molecule to myth tells us less about blood than it does about the human need to belong. In a quiet office in Tokyo, fluorescent lights humming above rows of identical desks, a manager distributes name tags for a team-building exercise. Each tag has a space for the employee's name and, beneath it, a smaller space for their blood type. Nobody questions this. Nobody finds it unusual. In Japan, blood type is not merely a medical detail. It is a social shorthand, a way of sorting people into categories as familiar and as casually deployed as zodiac signs in the West. The system is simple. Type A individuals are said to be earnest, organized, anxious, considerate. Type B are creative, passionate, selfish, unpredictable. Type O are confident, ambitious, natural leaders. Type AB are mysterious, rational, indecisive, a blend of contradictions. Walk into a bookstore in any Japanese city, and you will find shelves devoted to blood type compatibility guides, blood type diet plans, blood type parenting advice. Television shows discuss celebrity blood types with the same easy familiarity that American talk shows discuss astrological signs. The roots of this cultural phenomenon are darker than its modern surface suggests. In the 1920s, a Japanese professor named Takeji Furukawa published a paper linking blood type to temperament, drawing on ideas that were circulating in Europe at the time about the connection between biological markers and racial character. Those ideas were dangerous, entangled with the eugenics movement and the pseudo-scientific racism that would soon engulf the continent. Furukawa's work was discredited after the war, but the seed he planted did not die. It lay dormant in Japanese popular culture for decades, then resurfaced in the 1970s and 80s as entertainment rather than ideology. Repackaged as personality quizzes, dating advice, and light-hearted self-help. The transformation was remarkable. A theory born in the shadow of racial science became a party game, a first-date icebreaker, a way for strangers to find common ground. But ideas, even playful ones, have consequences. In Japan, a word exists for discrimination based on blood type, burahara, short for blood type harassment. The colleague who is not assigned a leadership role because type B personalities are said to lack discipline. The child teased in school for being too serious, too type A. The job applicant asked to list their blood type on a resume, as though 4 letters could reveal the architecture of a soul. Government agencies and scientific organizations in Japan have repeatedly issued statements reminding the public that there is no robust scientific evidence linking blood type to personality. Hundreds of studies, involving tens of thousands of participants, have searched for meaningful correlations and found none that survive rigorous analysis. When large meta-analyses combine the data from individual studies, the signals dissolve into noise. If blood type affects personality at all, the effect is so small that it vanishes beneath the weight of every other factor that shapes who a person is. On the other side of the world, a different but parallel phenomenon has been unfolding. In English-speaking countries, particularly in online communities that gather in forums and social media groups, Rh-negative blood has become the nucleus of an identity movement that combines elements of alternative science, spirituality, and the search for belonging. Where Japanese blood type culture focuses on the ABO system and treats all types as equal participants in a personality typology, Western Rh-negative culture focuses on the minus sign and treats it as a mark of distinction. Scroll through these communities, and you will find lists of alleged Rh-negative traits repeated with the conviction of liturgy. Higher intelligence, unusual eye colors, green, hazel, eyes that seem to change shade with mood or light, lower body temperature, sensitivity to sunlight, enhanced intuition, bordering in some accounts on psychic ability, a feeling of being different, of not quite fitting in, of sensing things that others miss. The lists vary from source to source, but the underlying message is consistent. Your blood makes you special. You are not like other people. There is a reason you have always felt this way. Some of these claims have a kernel of empirical reality, thin and fragile, but not entirely invented. A few small studies have found that Rh-negative individuals may, on average, have slightly lower blood pressure than Rh-positive individuals. The differences are modest and not universally replicated, but the finding is not fabricated from nothing. Light sensitivity and unusual eye color are more easily explained by shared ancestry than by blood type. Blue and green eyes, pale skin, and Rh-negative blood all cluster in the same Northern European and Atlantic populations, traveling together not because one causes the other, but because all 3 trace back to the same ancestral gene pool. The intelligence claim is more fraught. A few studies, often small and methodologically limited, have been cited as evidence that Rh-negative individuals score higher on intelligence tests. When researchers examine larger populations and control for education, socioeconomic status, and geographic region, the alleged difference largely disappears. Intelligence is shaped by thousands of genes, by nutrition, by childhood environment, by educational opportunity, by the accumulated lottery of circumstance. The presence or absence of a single protein on red blood cells does not function as a master switch for cognitive ability. The psychic and empathic claims occupy a different category entirely. No controlled, replicable study has demonstrated enhanced extrasensory perception tied to the Rh factor. What has been demonstrated repeatedly is that people who already believe in paranormal phenomena are more likely to interpret ambiguous experiences as confirmation of their beliefs. A person who has been told that their blood type carries ancient, possibly otherworldly origins will notice every coincidence, every hunch that proves correct, every dream that seems prophetic, and file it as evidence. The misses are forgotten, the hits are remembered. The identity circularly confirms itself. Psychologists have a name for the mechanism that underlies much of blood-type personality belief. The Barnum effect, named after the showman who understood that a sufficiently vague compliment will be accepted by almost anyone as a personal truth. You are sometimes shy, but you can also be outgoing in the right situation. You care deeply about others, but you wish they understood you better. You have creative abilities that you have not fully explored. These statements feel precise. They feel tailored. They fit almost every person who reads them, regardless of blood type, zodiac sign, or any other categorical label. But to dismiss these beliefs as mere superstition is to miss something important about why they persist. Being Rh negative can feel like belonging to a small, invisible club. In many populations, only a fraction of the people you meet share your blood type. Rarity invites meaning. When something about you is uncommon, the question why arises naturally. And in a world where traditional markers of identity, village, extended family, religious community, stable profession have weakened or dissolved, a biological label can feel like an anchor. The stories that gather around Rh negative blood serve a function that science, with its insistence on probability and its allergy to narrative, cannot easily provide. They tell people who they are. They explain why they feel different. They connect the isolated individual to a larger story, a lineage of survivors, an ancient bloodline, a hidden heritage that makes the loneliness of modern life feel like a misunderstood gift rather than a meaningless accident. In Japan, the same need finds expression through a different system. The ABO personality types offer categories, communities, conversation starters. They give people a language for talking about temperament and compatibility without the vulnerability of genuine self-disclosure. You are type A, so of course you worry. I am type B, so of course I am unpredictable. The categories simplify. The simplification comforts, and the comfort persists even when the science behind it has been thoroughly dismantled. What both phenomena share, East and West, is the ancient human instinct for classification. For hundreds of thousands of years, survival depended on sorting the world into patterns. Safe and dangerous, friend and stranger, edible and poisonous. As societies grew beyond the scale where every individual could be known personally, shortcuts became necessary. Tribe and outsider, clan and rival, noble and common. In the modern world, those shortcuts have taken new forms. Zodiac signs, personality tests, political affiliations. The house your favorite quiz assigns you in a fictional school of magic. Blood type fits neatly into this instinct. It is invisible, mysterious, and yet precisely labeled. One letter, one sign. A tiny fragment of biology that can be inflated into a complete personality sketch. It offers what the human mind craves most deeply. A sense that the self is not arbitrary, that who you are is written somewhere, in your cells, in your stars, in the ancient code of your ancestors, that there is a reason for everything, even for the quiet sense of not belonging that visits everyone. regardless of blood type, in the small hours of the night. The challenge is to hold two truths at once. The first is that Rh-negative blood is a real biological variant with real medical implications, a trait that connects millions of living people to an ancient and genuinely mysterious chapter of human history. The second is that the stories we tell about that trait, the superpowers, the cosmic lineages, the personality profiles, say more about the storytellers than about the blood itself. They reveal our longing for patterns in chaos, for significance in randomness, for a story grand enough to explain why we feel the way we feel. In the end, the molecules in your blood do not dictate your kindness or your courage, your creativity or your fear. They do not predetermine your destiny. But the stories you tell about those molecules, the meaning you choose to find in them, the communities you build around shared labels and shared wonder, those can shape how you move through the world. The blood is real, the meaning is made, and both, in their own way, are part of what it means to be human. Chapter 11. The Scarce River. In a hospital at 3 in the morning, when the lights are bright and the clock is merciless, a bag of blood hanging from a metal stand can be the difference between a life that continues and one that does not. And sometimes the rarest blood is the only kind that will do. The ambulance arrives without warning. Tires hiss against wet pavement, doors slam open, and a stretcher rolls through the emergency department entrance, trailing the urgent shorthand of paramedics relaying information to nurses who are already moving. Car accident, massive blood loss, no identification, no medical history, no time. In the seconds that follow, before anyone knows this person's name, before their family has been called, before the surgeon has scrubbed in, one question rises above every other. What blood can we put into their veins without killing them? The laboratory is minutes away from a full cross-match. The patient is seconds away from hemorrhagic shock. Someone has to make a decision with incomplete information and absolute consequences. This is the moment when Rh-negative blood steps out of the shadows of genetic mystery and becomes something else entirely. Not a cosmic anomaly, not a mark of ancient lineage, a working tool, a medical lifeline measured in milliliters and minutes. In the cold storage of the hospital blood bank, one shelf is treated with particular reverence, inventoried more carefully, restocked more urgently, guarded more anxiously than any other. The shelf labeled O-negative. O-negative blood carries no A antigens, no B antigens, and no Rhd antigen. To most immune systems, it is the least threatening stranger in the room. In an emergency, when there is no time to test and match, O-negative is the closest thing medicine has to a universal key. It can be transfused into almost anyone without triggering the immediate, catastrophic immune reactions that kill patients within minutes of receiving incompatible blood. The word almost carries weight. Human red blood cells are not defined by the ABO and Rh systems alone. They carry dozens of additional antigen systems with names that sound like characters from a half-forgotten novel. Kell, Duffy, Kidd, MNS, Lutheran, Lewis. Each system can, in theory, provoke an immune response. A patient who has received multiple transfusions over the course of a chronic illness may develop antibodies against several of these minor antigens, narrowing the pool of compatible donors to a handful of people scattered across an entire country. For such patients, even O-negative blood is not safe enough. They need blood matched, not just on the 2 major systems, but across half a dozen minor ones. A combination so specific that finding a compatible donor can take days of searching through regional and national databases. These are the patients whose blood type is described, without exaggeration, as rare. The patients, for whom a single compatible unit of blood might need to be flown across state lines, packed in ice, tracked by phone call and courier, arriving at the hospital with the urgency of a transplant organ. But for the vast majority of emergency transfusions, O-negative remains the standard. The break glass in case of emergency blood that every trauma center keeps on hand, counted and recounted, rationed and protected. The problem is that there is never enough of it. Rh-negative blood types make up roughly 15% of the population in regions of European descent, and O-negative specifically accounts for about 7%. Yet O-negative is the type most likely to be used in emergencies, in neonatal intensive care units, and for any patient whose Rh status is unknown. Blood donation organizations live with this imbalance as a permanent condition. They track their Rh-negative inventory the way a desert community tracks its water table, watching the levels, calculating the rate of consumption, measuring how long the supply will last before the next donation drive replenishes it. Targeted campaigns appear regularly in newspapers and on social media. O-negative donors urgently needed. Your blood type is rare and in high demand. Please consider donating today. The donors who respond to these calls carry a quiet logistical value that most of them never think about. A single donation of O-negative blood, roughly 1 pint, drawn from a vein in the crook of an arm over the course of 10 minutes, can be separated into components: red cells, plasma, platelets, each directed to a different patient with a different need. The red cells might go to a trauma victim in the emergency department. The plasma might go to a burn patient in the intensive care unit. The platelets might go to a child undergoing chemotherapy, whose bone marrow has temporarily stopped producing its own. For Rh-negative individuals who are not O-negative, the logistics are slightly different but equally important. A-negative, B-negative. AB-negative blood is less commonly needed in emergencies but essential for the Rh-negative patients who require type-specific transfusions. An Rh-negative woman of childbearing age, in particular, must receive Rh-negative blood whenever possible, because a transfusion of Rh-positive blood could sensitize her immune system and create the very antibodies that ROGAM was designed to prevent. For her, the wrong transfusion today could mean a dangerous pregnancy tomorrow. The fragility of this system became visible during the early months of the pandemic in 2020, when blood donation centers across the world saw their appointments plummet. Social distancing measures, lockdowns, fear of infection in clinical settings, all conspired to reduce the flow of donated blood at precisely the moment when hospitals were filling with critically ill patients. Blood banks that had operated with thin margins suddenly found themselves rationing, prioritizing, making calculations that no one wanted to make. Which patient gets the last unit of O-negative? The trauma victim or the premature infant? The answer depends on who is closer to dying, and sometimes both are equally close. The shortage is not limited to pandemics. It is structural, chronic, woven into the arithmetic of supply and demand. Blood has a shelf life. Red blood cells can be stored for approximately 42 days under refrigeration. After that, they must be discarded. There is no way to stockpile indefinitely, no strategic reserve that can be built up in good times and drawn down in bad. The supply must be constantly replenished by living donors, 1 arm at a time, 1 pint at a time, in a rhythm that must never stop. This reality has driven researchers to pursue what might be the most ambitious project in transfusion medicine: the creation of blood that does not come from a human donor at all. The idea is not new. Scientists have been working on blood substitutes for decades, exploring compounds that can carry oxygen through the body the way hemoglobin does, without the immunological complexity of real red blood cells. Hemoglobin-based oxygen carriers and perfluorocarbon emulsions have both been tested, with mixed results. Some showed promise in laboratory settings, but caused problems in clinical trials. None has yet replaced donated blood in routine medical practice. A different approach has gained momentum in recent years, one that does not try to imitate blood with synthetic chemicals, but instead grows real red blood cells in the laboratory, starting from stem cells. The concept is elegant in principle. Take a small sample of stem cells, the flexible, undifferentiated cells that can mature into many different tissue types. Place them in a nutrient solution that mimics the chemical environment of bone marrow. Coax them to differentiate into red blood cells, billions of them, identical and standardized, produced in bioreactors instead of bodies. In November of 2022, a clinical trial in the United Kingdom marked a milestone. The RESTORE trial, a collaboration between the National Health Service Blood and Transplant Service, the University of Bristol, and the National Institute for Health and Care Research in Cambridge, performed the first transfusions of laboratory-grown red blood cells into human volunteers. The doses were tiny, approximately 2 teaspoons of lab-grown cells per transfusion, and the trial was designed to test safety and cell longevity rather than therapeutic efficacy. But the symbolism was enormous. For the first time in history, red blood cells manufactured outside a human body were circulating inside one. The challenges ahead are vast. Cost remains prohibitive. Early estimates place the price of a single unit of lab-grown blood at tens of thousands of dollars, though advances in production methods have brought that figure down significantly. Scale is another obstacle. A single blood transfusion requires hundreds of billions of red blood cells. Producing them in quantities sufficient to supply even a fraction of the world's transfusion needs would require bioreactors on an industrial scale, operating with a precision and reliability that current technology has not yet achieved. But if the technology matures, if the costs fall, if the production challenges are solved, the implications for Rh-negative blood would be profound. Engineers could design lab-grown red cells to lack specific antigens, creating something close to a truly universal blood product. The chronic shortage of O-negative donations could be relieved. Patients with rare antigen combinations, the ones who currently wait days for a compatible match, could receive custom-manufactured blood tailored to their immunological profile. Even in this imagined future, Rh-negative blood would not become irrelevant. The genetic and immunological knowledge needed to design universal blood cells comes from studying the full spectrum of human blood diversity, including the rare variants. Rh-negative blood, with its stripped-down antigen profile, serves as a template, a reference point for understanding how to minimize immune reactions. The people who carry this trait today are not just patients and donors. They are living libraries of biological information, carrying in their veins a variation that helps researchers understand the boundaries of immune tolerance. Tonight, somewhere in the world, an O-negative donor is sitting in a reclining chair with a needle in their arm, watching a bag slowly fill with dark red blood. They may not think of themselves as part of a living infrastructure. They may not know that the bag hanging beside them will be separated into components, tested, labeled, stored, and eventually hung from a metal stand in a room where someone's life depends on it. They are performing a quiet act of continuity, a modern echo of the ancient networks of cooperation that carried our ancestors through ice ages and famines and plagues. The blood that flows from their vein into the plastic tubing is the same blood that puzzled Landsteiner and Wiener in 1940. The same blood that killed babies before Frieda and Gorman found a way to stop it. The same blood that clusters in the mountains of the Pyrenees and along the Atlantic fringe of Europe, carrying within it a story that stretches back tens of thousands of years. In the clinical brightness of a modern donation center, under fluorescent lights and the hum of refrigeration units, that ancient story continues, one pint at a time, one heartbeat at a time, flowing from the deep past into the uncertain future. Chapter 12. Still flowing. The mystery began long before hospitals, before microscopes, before anyone knew that blood came in types. It will continue long after the last page of this story fades into the quiet of sleep. The room around you is dark now, or nearly so. Perhaps there is a faint glow from a screen, a thin line of light beneath a door, the distant hum of a city settling into its late-night rhythm. Your breathing has slowed. The pillow has found its shape. And the story that began in a New York laboratory 86 years ago has wound its way through centuries and continents. Through mountain villages and palace corridors, through microscopes and maternity wards, to arrive here, in the stillness where all stories end. Let the facts settle gently, like sediment drifting to the bottom of a quiet river. In 1940, two men noticed that 15% of human blood lacked a protein that every other primate carried. In 1939, a young mother's body rejected her own husband's blood after delivering a stillborn child, and an immunohematologist began to understand why. For decades before anyone knew what was happening, mothers lost baby after baby to an invisible war between immune systems, and no one could tell them why. Then a simple injection, a borrowed set of antibodies, slipped into a mother's bloodstream at the right moment, silenced that war entirely. The babies lived, the mothers were spared, and the trait that had caused the suffering remained, common as ever, concentrated in the mountains and coastal fringes of Western Europe, carried silently by one in every 6 or 7 people on Earth. Nobody fully knows why it persists. The mainstream explanation offers mutation, drift, and the slow mathematics of population genetics. Forces that operate beneath the threshold of human perception, shaping the species across millennia without anyone noticing. A few researchers have found tantalizing hints of hidden advantage. Subtle interactions with parasites, modest shifts in disease susceptibility, the faint shadow of a benefit too small to measure with certainty, but perhaps large enough, over tens of thousands of years, to keep the trait alive. Others have looked at the same evidence and seen different shapes in the shadow. Ancient lineages, lost civilizations, divine intervention. Sacred bloodlines preserved by mountain and ocean, while the rest of humanity mixed and moved and forgot. These stories cannot be proven. Most of them conflict with what the evidence actually shows. But they persist because they answer a question that science has not yet fully closed. And because the human mind, confronted with a genuine mystery, will always prefer a meaningful story to an honest silence. The truth probably lies somewhere quieter than any of these narratives suggest. Human genetics is not a novel. It does not organize itself into tidy plots with clear beginnings and satisfying endings. It is messy, contingent, shaped by accidents of geography and climate, and the random shuffling of chromosomes during reproduction. Sometimes a trait persists because it provides a decisive advantage. Sometimes it persists because the cost of eliminating it is not quite high enough to overcome the inertia of inheritance. and sometimes it persists because the species simply has not had enough time or enough pressure to resolve the question one way or the other. What is certain is that the story is not over. In laboratories around the world, new tools are pushing the boundaries of what can be known. Ancient DNA extraction grows more refined each year, pulling fragments of genetic information from bones that have lain in the earth for tens of thousands of years. Researchers can now trace the Rh-negative deletion across prehistoric populations, watching it appear and spread like embers carried by the wind across a dark landscape. Large-scale genomic studies, analyzing the DNA of millions of living people, are building maps of human variation more detailed than anything previous generations could have imagined. Somewhere in those maps, in the dense thicket of data points and statistical models, the answer to the evolutionary paradox may already be hiding. Perhaps it will emerge as a clear and decisive finding. A single pathogen or selective pressure that explains the persistence of the RhD deletion, as neatly as the sickle cell allele explains malaria resistance. Perhaps it will arrive as something more diffuse, a web of small advantages and complex interactions that resist reduction to a single story. Perhaps it will surprise everyone, revealing a mechanism that no one has yet proposed, hiding in plain sight the way the Rh factor itself hid for decades in blood that doctors had been transfusing since the 19th century. In the Basque Country, the mountains still rise in the morning mist, and the language that has no relatives is still spoken around kitchen tables where bread is broken and wine is poured. The blood that flows through those hands is the same blood that flowed through the hands that painted bison on cave walls 20,000 years ago, in the same valleys, under the same stars, in a continuity so deep that the word ancient barely begins to describe it. In hospitals tonight, bags of O-negative blood hang from metal stands, dripping quietly into the veins of people who will never know the name of the donor who gave it. In neonatal wards, tiny infants born to Rh-negative mothers sleep peacefully in plastic bassinets, their blood undisturbed by maternal antibodies, protected by an injection that their grandmother's generation could never have imagined. In donation centers, chairs sit empty, waiting for tomorrow's volunteers. The quiet infrastructure of a species that has learned, after millennia of trial and error, how to protect itself from its own biology. In a laboratory in Bristol, a culture dish holds a thin layer of red liquid, cells grown from stem cells, coaxed into becoming something that might one day flow through veins without the need for a living donor. The technology is young, expensive, unproven at scale, but the ambition behind it is as old as medicine itself, to keep people alive when their own bodies fail them. And the template for that ambition, the baseline against which all artificial blood must be measured, is the same stripped-down, antigen-sparse, immunologically quiet red blood cell that Landsteiner and Wiener first noticed 86 years ago. The cell that lacks the one protein that almost every other primate on Earth possesses. Your own blood, whatever type it carries, is performing its work right now, in the darkness, without instruction or encouragement. Red cells are picking up oxygen in your lungs and carrying it to your fingertips, your toes, the furthest reaches of your body. White cells are patrolling, scanning, checking for invaders. Platelets are standing ready, prepared to seal any breach in the walls of your vessels. The whole system runs with a precision so ordinary that you never think about it. A quiet miracle repeated with every heartbeat, every breath, every slow descent into sleep. Whether your Rh factor is positive or negative, whether your type is A or B or O or AB, the blood in your veins carries the same fundamental story. A story of survival, of ancestors who endured ice ages and famines and plagues and migrations, and the ordinary, relentless difficulty of staying alive long enough to have children who could carry the story forward. Every person breathing on this planet tonight is the product of an unbroken chain of successful reproductions stretching back hundreds of thousands of years, an unbroken chain of heartbeats, each one handing the work to the next, never stopping, never pausing, from the first campfires on the African savanna to the glow of the screen in your darkened room. Some of those ancestors carried the Rh protein on their red blood cells, and some did not. Some lived in mountains, and some lived on plains. Some spoke languages that survive today, and some spoke tongues that vanished so completely that not a single word remains. What they shared was the thing that you share with every other human being alive tonight. A body that works, a heart that beats, blood that flows, and the accumulated inheritance of a species that has come very close to extinction more than once, and somehow, through luck and stubbornness and the slow, blind genius of evolution, is still here. The mystery of Rh-negative blood is real. The science is incomplete. The questions remain open. But the fact that you are alive to wonder about them, that your blood is circulating through your body right now, carrying oxygen to the brain that is processing these words and turning them into images and feelings, and the slow, gentle slide towards sleep, that fact alone is the deepest answer the story has to offer. You are here. Your blood is working. The chain is unbroken. Outside your window, the world has gone quiet. The city has dimmed, or the countryside has settled into its deepest silence, or the rain has started, soft and steady, the kind that makes the darkness feel like a blanket rather than an absence. Whatever questions remain about the protein on a red blood cell, whatever theories and speculations and late-night arguments continue to swirl around this strange, persistent, beautiful anomaly in human biology, they can wait until morning. They have waited tens of thousands of years already. They can wait one more night. Rest now. Let the story settle. Let the images fade, the laboratories and the mountain villages, the maternity wards and the ancient caves, the test tubes and the thrones and the quiet donation centers where ordinary people give something irreplaceable to strangers they will never meet. Let it all drift away, carried downstream by the same slow current that carries everything eventually towards sleep. Your heart is beating, your blood is flowing. The mystery endures, half solved, half hidden, circulating in silence through millions of hearts around the world. And tonight, it carries you gently toward whatever dreams are waiting. If this story kept you company, if it made the darkness feel a little less empty and the hours a little shorter, you might consider a gentle tap on the like button or a quiet subscription, so the next story will be here when you need it. No rush, no pressure. Just a door left open for the next time sleep needs a companion. Good night, rest well, the blood remembers, the story continues, and you, whoever you are, wherever you are part of it.